Hey YouTube, how's it going? YakScience here with another OChem video. Today we're going to be talking about Electrophilic Aromatic Substitution, or EAS for short. Now you can tell a lot from the name. We can see that in this class of reactions, we're going to be substituting an electrophile onto an aromatic compound like benzene, for instance. Okay, so anytime we want to replace one of the hydrogens on benzene with, let's say, a Br or a Cl or maybe an alkyl group, right? You're going to use EAS mechanisms. So in this video, I just want to go over the general EAS mechanism that'll be true for pretty much all EAS reactions. So let's get started. All right, so here I've drawn benzene. Benzene is an aromatic compound and is very, very stable. What that means is if we want to add something onto this benzene ring, we need an electrophile that's really, really strong. It has to be strong enough to disturb the aromaticity of benzene. So let's say for the purposes of this video, you take an arbitrary, really strong electrophile, let's call it E. And notice that I gave our electrophile a positive charge because most, if not all, strong electrophiles will have a positive formal charge. So what will happen in an EAS reaction is remember a pi bond could serve as a nucleophile, right? So one of the pi bonds in the benzene or in the aromatic compound that you're working with will nucleophilically attack the electrophile. Okay, so that'll get us here. Notice that we have successfully added or substituted our electrophile onto the ring. It's right here as E, but also notice that we're left with a carbocation, and that's because we took that electron away from this carbon and disturbed the aromaticity of benzene. Okay, so the next step has to involve getting that aromaticity back, restoring it. And that'll involve some acid-base chemistry. So let's introduce an arbitrary base, let's call it B. So our base B is actually going to deprotonate this hydrogen right here, the hydrogen that's on the same carbon as the electrophile that we just substituted on. And then the electrons in that carbon-hydrogen bond will collapse and go back to restore the aromaticity by reforming that pi bond. It'll look like this, right? So now that'll get us here. So notice that we still have our electrophile substituted onto the ring. We've restored our aromaticity, right, by reforming that pi bond. And we formed the conjugate acid, right, HB of the base that we used in the previous step. And so that's how we get an arbitrary electrophile E onto a ring. Most of the reactions will also involve a catalyst, right? But for now, I just wanted to give you the general mechanism. So I hope that was helpful, and thanks for watching.